Thank you very much. I also would like to thank the organizers for the kind invitation. It's very nice to be here for interesting talks and very beautiful surroundings. So what I would like to present in this talk is a class of time integrators, which is probably not so well known. Just to start with the general format of the method. So in principle, the situation is a very simple one. We just have a linear differential equation. Maybe to start first with applications. So you can think of Schrödinger type equations where this arises. So you have a time-dependent Hamiltonian operator. We saw this in the last days in several talks where such a problem arose as a part of the problem. So you can also think of a building block, yeah? And you have in additional a nonlinear term, which you could treat by additional splitting methods. Okay, of course, also parabolic equations are of interest. And so these will be PDEs, and somehow a simpler situation where you just can think of a matrix, in this case, quantum systems with or without dissipation. Okay, and not to forget the method. So what is the general form of the method? So you have your matrix or operator with explicit time dependency defining the differential equation. And the basic idea is that you pick some nodes. So usually these will be quadrature nodes, in particular Gaussian quadrature nodes. You evaluate the matrix at these points, and then you build linear combinations of these functions, of these matrices, and then you compute the exponentials of such linear combinations, and you combine it, and with this you can construct methods of higher order. Yeah? So you can increase the accuracy of your computations. In this talk I will mainly focus on practical aspects, so we constructed novel schemes which are favorable in the non-dissipative case, but also when you have some dissipation in the system. So I would like to start with a very simple test equation, which is of parabolic type. And in this case, you can think of a nonlinear equation you start with. So we have some diffusion term, possibly an additional nonlinearity in front, possibly a nonlinear advection term, and some reaction term. And in order to prescribe the solution, I'm also adding this inhomogeneity. And when you compute the associated variational equations, so for instance, the equation, so the derivative of the solution with respect to the initial value, you will arrive at a problem which has the form we are studying. So we have just certain coefficients which will in general be space-dependent and time-dependent. Yeah? Okay, and to make the situation very simple, I impose periodic boundary conditions, so I have no effect from the boundary conditions, so no order reductions from the boundary conditions. In particular, I also assume that my solution is sufficiently regular in order to obtain higher order methods, yeah? to observe higher order. Okay, and for this particular situation, I indeed have a problem of parabolic type. You see the diffusion in the equation, in this solution profile. And then, starting from this test equation, I apply different methods, methods of different orders. So in particular, second order method, fourth order method, fifth order method, and sixth order methods. And in all cases, I will choose the spatial grid width sufficiently small so that the error comes from the time discretization. Yeah? Okay. And at first, you will look at the accuracy of the schemes. So you display the global errors versus the time step sizes. But what is even more important is the efficiency of your schemes. So you somehow need to measure the cost of these methods. And in this first test situation, I do it in a very simple way. I just count the number of exponentials, but this should be refined. You should find a more clever way. Since, of course, the computation of the matrix exponential is the essential point than in applications. Okay, and I'm already saying this. We have a better indicator for efficiency for a quantum system with this dissipation, and then our methods perform even better. Okay, I hope you can see it clearly. So, for instance, here we have a second-order scheme. I compare it with the case where I chose slightly different quadrature nodes. So this can be nice for accuracy, but also for the efficiency of the method. Then I have the simplest second-order method. I will display it later on. This is, let's say, the first starting point to construct the fourth-order scheme. And then you have improved methods. Yeah? And in particular, we compared our scheme with a fourth-order scheme constructed, optimized by Albermann and Feske. And you see that, let's say, in this situation, all methods are rather close, and in particular, and also for efficiency. Okay, there's one drawback of the methods constructed by Albermann and Feske. So they involve negative coefficients, and you know that when you solve the diffusion equation backward in time, then you have instability. So a lack of well-definedness for the methods. And this you see in this situation. So you see this instability here. Yeah? And so these methods are, of course, also not efficient for parabolic problems of parabolic type. Okay, and in this case, really the new methods we found were more efficient in all cases. Okay, just to say, it's probably not clearly seen. So this is second order, fourth order, and these are methods of order 5 and 6, so of higher order. Okay, so what we see in this situation, so we have a smooth initial value, we have periodic boundary conditions, so we have a smooth exact solution. So our integrators retain their non-stiff orders of convergence. So we have very nice accuracy, no order reductions. And what is also obvious here, that we have a poor stability behavior of certain schemes involving negative coefficients. Yeah, and this was somehow the motivation, our starting point. Okay, so what was our guideline? First, we wanted to understand what are really the stability issues, or how can you overcome them. So we started with the stability and error analysis of these kind of methods. We did, well, of course, you have to for the analysis you have to distinguish different classes. So we looked at Schrödinger equations, and we recently completed a work on parabolic equations. So for this, we really have the rigorous analysis for high order methods for the general case. Okay, and what is, of course, of interest for practical purposes is the construction of schemes to build the order conditions and to resolve them. And this is joint work. So both this joint work with my colleagues from Spain, Sergio Blanes and Fernando Casas. Okay, so maybe to put this into some context, so what was our starting point? So we had a look at the papers by Albermann and Feske, and Littlewood, where they have quantum systems with and without dissipation, and their aim was to construct new schemes, to optimize, to find optimized schemes, so with high efficiency. Then there was previous work by my colleagues, by Sergio and by Christian Mon, and also by Sergio, Fernando, Otea, and Rose, concerning higher order methods, how to construct them, how to find a good way to represent the order conditions. And what I did several years ago was to provide an error analysis, but for a fourth order scheme, but in this case, I focused on order reductions you will encounter for Dirichlet boundary conditions, Neumann boundary conditions. So we had, let's say, some experience in this field. What I would like to present today is in particular the part on the design of novel schemes. present some numerical comparisons, and very briefly just to let's say, to show the theoretical convergence result, and to show numerical illustrations of different types. Okay, so, well, when you start with such a linear equation, non-autonomous linear equation, the usual approach would be the following. You would look for a representation of the solution. Yeah? And it is well known that in principle you can represent your solution in a complicated way, but still you can represent it as an infinite series of integrals of this form. So you have a first integral, which is just defined by the right-hand side, and then you have a double integral, which involves the commutator of the right-hand side. Yeah? And then, of course, your expressions become more and more complicated. So you have this kind of nested iterated commutators inside. When you have this expansion, a very natural idea is to construct numerical methods just to truncate the expansion at some point, for instance here, or maybe at the next term, and to apply quadrature formulas in order to approximate the integrals. Yeah? And this idea is used, and it leads to the class of interpolatory Magnus integrators. I call it in order to distinguish it from commutator-free integrators. And when you do this, so when you want to obtain a second-order method, you would apply the exponential midpoint rule. So what you do is you just look at the first integral, and you evaluate your function at the midpoint of the time interval, and then from the integration which is left, you have this additional time increment. So my notation will always be tau for the time increment, and Tn is the time where we start in order to construct then the new approximation at time Tn plus 1. Okay, so this is already quite a nice method, a second order method, and then you can of course do better by more complicated approximations. So here you would also involve the second order term. In principle, this is nice, but when you think of systems which involve large matrices, so when you have a large degree of freedom involved, it is very costly to realize these commutators. Yeah? You need a lot of memory and also computation in order to compute these matrix exponentials. You need to multiply a of Tn with the next one, and also in reversed order, and possibly you also have to save these matrices. So the presence of commutators is not so nice from the efficiency point of view. So you have a large computational cost. Okay, of course I should say how shall we realize the exponentials, and then there are of course different possibilities. For instance, we can think of Krylov type methods. So here the idea is to replace the exponential by matrix vector multiplications. Yeah, and then you have similar possibilities. It was also mentioned before, Chebyshev polynomials, so kind of interpolation, layer point interpolation, Taylor series expansions, or also you can use it. You could also use splitting methods, spectral methods in combination. Yeah. Okay. A second issue, this you see in the theoretical analysis, is the loss of structure. So assume that you have here some differential operator of second order. It's not clear how your commutator will look like. So this is some kind of, or in any case, it will have different properties than the original operator. So this is a kind of issue which you encounter then when you want to analyze the methods for PDEs, for evolution equations. And so the approach is to use related methods which do not involve these commutators, and they are called commutator-free Magnus integrators. And here there's also a nice citation given in the work by Alverman, Feske, and Littlewood. So we explain the use of commutator-free exponential time propagators for the numerical solution of the associated Schrödinger or master equations with a time-dependent Hamilton operator. These time propagators are based on the Magnus series, but avoid the computation of commutators, which make them suitable for the efficient propagation of systems with a large number of degrees of freedom. Okay, so this idea, well, it's not so obvious that these methods are really related, but we will, well, when you analyze them, you will see the relationship. What I would like to emphasize here is that, as I said before, the approach is the following. You keep the values, values at certain nodes, but the main difference is that you replace a single matrix, exponential, by several matrices, so by several exponentials, and the exponents involve linear combinations of these matrices coming from the evaluation at certain nodes. Okay, this as I said before, you might use Krylov type methods for the realization of these methods. And what is also interesting, so these methods are somehow very natural to be related to Magnus integrators, but they are also very natural to be related to time-splitting methods. When you add the trivial differential equation, the derivative of the time is equal to 1. So you somehow freeze time. Then you would have a scheme which has this form. So you see the only difference is that you just have one matrix involved and not a linear combination. And the advantage of this general format is that you can reduce the number of exponentials and so the cost. So in comparison to splitting methods, to the simple approach, the commutator-free Magnus integrators will be superior. They will be much cheaper. Yeah? And this is something that we will use. Okay, simple methods. So I gave this one before. This is just a second-order Magnus integrator, where we have one exponential, one quadrature node, and a natural extension to fourth order involving two exponentials. This is the following. So you could use the Gaussian quadrature nodes, so two Gaussian quadrature nodes. So we have a fourth order quadrature rule, and then you have certain coefficients involved, and then you build up these two exponentials. Yeah, okay. And this scheme is nice. It's nice for Schrödinger equations, and it's also nice for parabolic equations. And the reason is, so I mentioned the issue before, also in this case you have negative coefficients involved, but what matters is the combination of the coefficients, and these combinations are positive in this case. So it's a nice method for Schrödinger and for parabolic problems, for quantum systems and for driven quantum systems where you have dissipation. Okay, so if this condition, and this comes out from the analysis, is not valid, so if you have linear combinations which give a negative value, then you encounter these stability issues I mentioned before. Okay. So, and this is just an example to show this once more. When I apply a second order, fourth order, and sixth order method to the test equation from before, I nicely have second order, I nicely have fourth order, and then I have these stability issues. And what I compare here is the case when I have a spatial grid width of something over 50, so 50 grid points to 100 grid points. And of course, then your system gets stiffer and then the problems are more severe. So you can imagine in 2 and 3 dimensions, this will not be an option to use this kind of method, since you have to reduce the time step size drastically, so which is not really realistic. Okay. Yeah. So what we see, there's no rigorous proof since this is very delicate. But we tested it extensively, and what you see or what you conjecture is an order barrier for this commutator-free Magnus integrator. So your conjecture is that up to order 4 it will work nicely, but when you want to stick to real coefficients only, you have this drawback, these stability issues. And I mentioned that there is this connection to splitting methods, and in splitting methods, recently, or let's say in the last years, the idea was to, where you have a similar problem, the idea was to overcome these kind of problems by using complex coefficients, and so our idea is to use complex coefficients for parabolic problems, so to satisfy a certain positivity condition we need for stability reasons or well-definedness. Okay, maybe I can be very brief on this. You have natural assumptions. In order to have stability, you need some bounds on the time step sizes. You naturally will choose quadrature nodes for your nodes. You have very basic consistency conditions which come from considering the autonomous case, and then you have this additional condition in connection with parabolic equations. Okay, so how to construct new methods? This is not really an easy task. So you want to optimize the error constant. You want to optimize certain quantities. You have larger systems of equations, so several polynomial equations involved, and you look for solutions which satisfy additional constraints. So in our case, positivity constraints, or also only real solutions. So this task is not so easy. The first thing, okay, maybe I will just focus on a simple case. So let's say we want to construct fourth, fifth, and sixth order methods. We fix the number of quadrature nodes to 3, and we focus on the case p equal 4, so the order equal to 4 over 5, or 5, and by time symmetry, we then also achieve higher order methods, so methods of order 6. Okay, a crucial point is that you rewrite the general format of your scheme. So I have these 3 nodes involved in a suitable manner. So I just somehow reorder them using instead functions where the index indicates the order with respect to the time step size. And this is a nice way. Then you have this set of order. Then you receive this set of order conditions. They are independent and they are achieved by some algebraic, so let's say sophisticated algebraic tools. So you see in the first case, in the first line, it's rather simple. You just have a linear combination, and then you have polynomial equations for your systems. Yeah? And these are the 10 order conditions in order to achieve order 5. Okay, and as I said, in case you, in addition, impose time symmetry of the method, which is quite natural, you can further reduce the number of order conditions, so you go down to 7 order conditions, which you would like to treat, and which where the solutions should be optimized in a certain sense. So how to optimize? The approach we took was the following. We express the order conditions in terms of few coefficients. So somehow these are our 3 degrees, the 3 degrees of freedom, and we try to optimize them, to minimize then the amount by which higher order conditions, for instance, at order 7 are not satisfied. And this led to the schemes that I will show next. Okay, and to test the equations, or let's say we chose this rather simple system. So we have the following form. The Hamiltonian is given here. Looks a bit complicated, but let's say this is just would just be the usual Hamiltonian defined by Pauli matrices, and then you have here this additional term, and this corresponds to dissipation in the system. So what I will compare is the case delta equal to 0, no dissipation, to the case where delta is equal to 1/10, some number. Yeah, okay, and then we have a special choice of the functions involved. This system is nice. It's a very simple ordinary differential equation, so the implementation is rather straightforward. You still have the characteristics of Schrödinger equations or parabolic equations when you choose a slightly larger dimension, so you see instabilities. And what is also nice in this case, you can just use Taylor series expansions in order to compute the matrix exponentials, and low order approximations are sufficient. So we took 6 or up to 8 terms in general. Okay. And I will not give the coefficients of the schemes, but we have different classes, different families. The first family corresponds to order 4, and here we really would like to keep this positivity condition on the coefficients. And what we found are 2 methods which involve, so the lower index is the number of exponentials of stages involved, which involves 4 or 5 stages, and we compared it with the method by Alvermann and Feske, which I mentioned before, which involves 3 stages. So the interesting point is to see in which regimes do our methods perform well? Are they better in certain regimes? Are they, let's say, more expensive in other regimes? And what you see here is the following. So you have the logarithmic diagram of the error, the global errors, and here you count the number of matrix vector multiplications as an indicator for the cost. And you see here, this is the method by Alvermann and Feske, and for instance, in this case where I put delta equal to 0, so let the Schrödinger type, no dissipation inside. For higher tolerances, this method is quite nice, but as soon as you require lower, I should say, if you require the error to be smaller, so for higher, lower tolerances, one of our methods becomes better. Yeah? And the situation is a bit delicate in the sense that when you vary the parameters or the functions in the problem, then you have different behavior in these cases. So in this situation, I would say it's not so clear. So any of these 3 methods will perform quite well. So the difference is not so significant. Okay, so here I'm showing a scheme which is a bit outside of the general format of the usual scheme. What you see here is the usual form. So I have certain exponentials where the exponent is defined by linear combinations. And here I still allow one commutator. And this is not a contradiction, since in this case the crucial point is that my commutator is of higher order in the time step size. So it will be very cheap to compute the exponential of this commutator. Yeah? And so with this modification of the general format, we obtain the method of order 6, which involves these 6 exponentials, and the performance is quite nice. So here I'm comparing it with the 6-order method by Alvermann and Feske, and you see also in the non-dissipative case, this method we constructed is quite a nice one. It stays below, and then in particular when you have the stability issues, the method is much better. Yeah? So here you really need, you see the crucial limit for the time step size. Otherwise, you do not receive a reasonable result. And the last kind of methods, the last family of methods, was using complex coefficients for order 4. It was possible to have real coefficients, but now we are concerned with order 5 and order 6, and where we have this order barrier. And we found 3 methods. This is a bit of a miracle that this method exists with only 3 stages, 3 exponentials involved, and in particular, we expect them to be nice for problems with dissipation. Yeah, and you see here it's more clear for the complex coefficients. This is somehow a general feature. The methods with lower stages, number of stages, will be more efficient than the other ones. Yeah. Okay. So we have somehow a separation, and here it's just a slightly bit different for this case. B0 equal 1/2. Okay. So I have 10 minutes. Okay. But still, I will not give too many details about the numerical analysis. So we are using for the parabolic case, we are using a rather standard analytical framework. So we assume that the operators are defined on a common domain, that they are sectorial, uniformly sectorial. We have some technical assumptions on equivalence of norms. And then, in particular, we also need a regularity with respect to t. So we assume some Hölder continuity. Yeah, okay. And from this, for the sectorial operators, you have the associated analytic semagroup, so the evolution operators, and you have this representation by the Duhamel principle, or you can just call it the Cauchy's integral formula. Sorry, no, I mixed this. No, this is the Cauchy's integral formula. Okay. So, and this will be the general result. So you measure your error in some Banach space, typically L2. Yeah. Then you have the error coming from the initial condition, from the approximation of the initial state, and then for sufficiently regular solutions, you see the expected power of the time step size. So the smaller your time step size, the better the approximation you will get. So what else to say? So we completed this analysis for the parabolic case. For the Schrödinger case, in special situations where you have, I write it in this way, then I do not need to write the constants. So say your A of t comes from the Laplace operator and the time-dependent potential. You would like to have the optimal regularity conditions on the initial state, and this is more complicated when you want to do this in detail, and we completed this for a fourth order scheme. Yeah, the general case is a bit technical. Okay. So, yeah, and typically, so I'm giving just two cases. So this would be somehow the general case. For instance, you could work with continuous functions, and then your assumption on the initial value on the solution is that you need two p derivatives of the solution in order to get the full order of convergence. And for the Schrödinger case, which I just wrote down, when you have L2, for instance, then you have much weaker regularity requirements for the initial value for the solution. Okay, I think I will skip this and turn to the final illustration. So this is now the Schrödinger case, a Schrödinger equation with a time-dependent potential, so Laplace operator plus potential, and I considered a regular situation. So here you have the harmonic trap, the quadratic potential, and some sign, higher oscillating sign in front, and in the other, so okay, now the battery is over. And in the other case, in this case, you just have let's say a ball where the radius of the ball varies with time. Yeah, and this is somehow the potential is nice. So you just have constant values, but you have, of course, these jumps at the boundary of of the ball. And what is typical here, so for the left-hand side, you just obtain the full order, and you have order reductions for the other case. But what you see here for efficiency and similarly for the cost, your higher order schemes can still be nice. So they are, although the order drops, their accuracy is still quite nice. Yeah, so I can achieve a better accuracy. Okay, and to hope it works. Just to give you an impression of this example. So this is the one with the non-smooth potential, and what is nice here, that at some point patterns form. So your solution reaches the boundary, I'm imposing periodic boundary conditions. And then I have a very nice pattern formation. It's a very nice profile of the solution. Maybe just once more. So at some point you reach the boundary, and then you have this, the periodicity of the imposed periodic boundary conditions causing these reflections, I will call it. Okay. And this was just, let's say, a try. So I was a bit fascinated by these nice patterns which formed. And I was curious whether this profile is stable, and it is indeed. So I used here a higher order method of order 4, in order to realize the exponentials, the matrix exponentials. And I computed it in the left picture with time step size 1/2, so a rather large time step size, and then with a much smaller time step size of 1/100, and you see practically no difference in the solution. Yeah? Okay. And also with the lower order method, you still keep this profile, and this is just to see how the solution evolves in time. So at some point, your external potential is just constant, and then you have just the evolution, of the free equation. Okay, to conclude, so what I would like to point out is these commutator-free Magnus integrators are probably not well known, but they provide a favorable alternative. They keep the structure of the system. They are less computationally costly, in particular for higher degrees of freedom. And you can also construct methods which are good for stability for parabolic problems. Yeah? And what remains somehow open is to finish the case of the Schrödinger equation from the error analysis and the application to more challenging applications. Yeah, and as I mentioned in the beginning, you can also think of these non-autonomous linear systems arising as a part of a nonlinear system. And then you could treat this with time splitting. So you keep the B part, you still, for Schrödinger equations, you still have this nice invariance property, and you just use the commutator-free methods for the first linear part. Okay, that's all. Thank you very much.
Thank you, Mechthild, for this nice talk. Are there any questions or comments?
At some point in your assumptions, you had only Hölder continuity of A of t.
Yeah.
But I guess that then any integrator is bound to theta to the power p.
This is for stability. So you have stability of the method under these assumptions, and then in order to have the full order of convergence, you need the solution to be sufficiently smooth, and this, of course, is also then, let's say, encoded in the operators, in the continuity of the operators. Yeah.
Any other questions? So you spoke about order reduction coming from the boundary condition. Do you have the same problem as splitting method with?
Yeah, essentially. So the problem is just that usually, let's say for Dirichlet conditions, you cannot assume that spatial derivatives of the solution belong then to or satisfy the boundary conditions. Yeah, and so, but I think this has been observed many, many times, and this is also the case for these kind of exponential methods. Mm-hmm.
No other questions? Yes.
Typically, when we do simulations with Gross-Pitayevsky, we want to know if conserve norm, if conserve energy. How about your integrators in this sense?
Yeah, so they are symplectic integrators. So in any case, you will have mass conservation. I did not try about energy conservation, but I assume it's very similar to splitting methods. So you should have a nice conservation properties. Yeah.
Other question? So, thank you again, Mechthild.